This is my project 2. Okay, let's look at task 1. So it says first thing is I have to do it for stereo 1 left and stereo 1 right. So yeah, it's already changed, and then I have to find 8 pairs of 2D points manually and then list them as G matching left and right. Okay, so for this what I did is I used Photoshop for getting the X and Y coordinates. So something like this. So this is my image, and then I just selected this pixel, and then we can see that our X and Y values are 95 and 518. So yeah, that's how I stored it in this xpix8 for the X values and ypix8 for the Y values. I've stored it in an array right now because I need to normalize them. So yeah, that's the second point. I normalized the coordinates and then I stored them. How did I normalize them? So I used this formula, which is the x position is put x into x scale, which is 2.0f divided by the canvas size. And yeah, this is how I use it. It's the same formula as the one here. So x into x scale, which is x into 2 divided by the canvas size, and it's the same for the y. Let's look at it. Yeah, 1 minus divided by image height and image width, which is the same as with the picture size, which is in our case it's 1000. It's 1000. That was my normalized coordinates function, and then I stored it in G matching left, and using a for loop I fit it into the 8 into 2 matrix. And yeah, I've even printed the value since I need it in a later part. So this is how it looks currently. These are my 8 matching points: 1 2 3 4 5 6 7 8. Now for task 2. Oh, also I tried to apply match finding algorithms, sift and superglue. So I tried 5 of them. Only 3 gave me results, and 2 I was not able to get them running. But even the working results are not really great. So let's look at sift. This is how there's just one line, and even that it's not matched correctly. This is the results from sift. Then I used orb. Orb also gave me 1 result, and even that's not matched properly. Now accelerated Kaze. These gave me a lot of points, but I don't think any of them are matched correctly. Then for superglue, I could not get it running because it keeps giving me an error. I've even downloaded the module, but I can't get it running. And I tried soft too, but soft, it's giving me some error with OpenCV. It says I don't have it, but it's working for Swift. That's very funny. For question 2, using those 8 matched points, now I have to calculate the fundamental matrix, which is the same as the essential matrix, and store it in G epipolar E. Okay, let's look at. Okay, so first thing is I decided to use the Kronecker product to design my matrix. and then we use SVD to break the matrix into three matrices again, which is U, sigma, and V transpose T. And the essential matrix or the fundamental matrix is the column of V, which is corresponding to the smallest singular value. So I tried implementing it in the same code, but has to. Okay, so this is my first method. So these are the matching points which I had found earlier. So matching points, here is my matrix, here is I perform SVD, and then here I try to store the column of V, which is corresponding to the smallest singular value, which is my essential matrix. But my error here is it says its reshape is not in this eigen library. So I tried changing it to resize, but then I'm getting a new error. It says no overloaded function. So I decided to not use this method. Now in method 2, I decided to store the values manually instead of using resize. Now my error here is, oh, there's no error, but the epipolar line is this blue line on top, so I don't know what's wrong with that. Okay, so this failed too. And another method I tried is to store it. Where is it? I tried to store the values manually like this and to design the matrix, but then I get another error, which is I mix matrices of different sizes. So I have no idea why it's not working on C++. So what I did is I used Python instead, and to calculate the essential matrix. So here I do the chronic product and then store it in matrix to design my matrix, and it's stored as and since we flatten it, so it's stored as one whole row, and then I perform SVD on it, and this is the V matrix which we need, and then the last column of the V matrix is stored as the essential matrix, and then it's reshaped again as a 3x3 matrix, and these are the values I got. So using those values I'm able to do this product. This is the result, and I think it's correct since it's the one which looks very similar to the one in the question. So that's it for task 2. Now for task 3, let me refer to the PDF. Question 3, what does line 382 to 389 do? And this for loop is actually the 382 to 389, but since I added some functions, the line number got changed. So it's this for loop. So let's try to understand this. It's a test for the epipolar line. And Yeah, let's see. So results were stored in G epipolar E, and we are going to use that to calculate the epipolar line. So here the essential matrix G epipolar E, which is our essential matrix. It's a 3 into 3 matrix which encodes epipolar geometry. And what we need to see is that it represents an epipolar line using the equation ax plus by plus c equal to 0. So yeah, this is just a way to check our epipolar lines. So this is basically a into x and then b into x plus c. I'm not sure why is there into 1 though. And this is just the line equation basically. And the line equation is our epipolar line which we got from our essential matrix. So it's even mentioned multiplying by the essential matrix will tell us the epipolar line. And since it's a line equation, so it should be close to 0. That's the second part. Why should all of the multiply values be close to 0? Where is it? Yeah, because it's the line equation. See, x into transpose L is equal to 0. Now for the fourth task, I have to go to this module, and so basically fundamental.cc and projection.cc. So the first question is explain fundamental from essential function. So let's look at my PowerPoint. So first thing is that this is all in the lib mv folder which I downloaded, and it's the library for multi-view geometry. So basically these are all functions that we use in multi-view geometry. Now let's look at the first function. So it's basically using the formula for calculating the fundamental matrix from the essential matrix, which is f is equal to k inverse t, a k inverse k dash inverse. Now how we got that? Okay, this is from the book which was mentioned to be referred to, and so let's break this down. So first is we have P, which is our camera matrix, and then we have this essential matrix formula which is translation into rotation matrix, and from another equation is x hat dash transpose E x hat is equal to 0. Okay, what does that mean? So x hat is equal to k inverse x, and x hat dash is equal to k dash inverse x dash. Okay, that still does not really make sense. So x dash is basically our homogeneous 2D point, and k inverse x is our 2D pixel coordinate, and then there is x dash, which is 3D scene point with respect to the second camera. And then using that formula we substitute x hat and x hat dash, and we get the formula for the essential matrix. And then we just go back to our original formula, and that's how we got our fundamental matrix formula, and it's what they have just applied in fundamental from essential function. Now let's look at motion from essential. Motion from okay, so this is the code. Let's go back to my PPT. Okay, so let's break down this code. This was what is told to be referred to in the book, and let's first look at this part. So what are the parameters? uh, and we can see they are using Jacobi SVD, singular value decomposition. Your E is our essential matrix, RS is our rotation matrix, TS is our translation vector. And if you remember from SVD, what we had studied is it breaks it down into U, sigma, and V. Now that's what it's doing, USVD, and we have VT again over here. And then over here they are checking to make or to define that our determinant is positive. Why? Because if the rotation matrix is valid, it should have a determinant of +1, or it should be positive. Then we look at this part, this U underscore W underscore VT. So, and W is our skew symmetric matrix, and these are our two new possible rotation matrices, and then we store the rotation and translation vectors. So that's why this second function is called motion, because we are performing rotation and translation and using the essential matrix. Now let's look at part 3, which is P underscore from KRT. uh, it's in projection matrix, so it's the first function, very first function. So this is just basically going to help us create a camera matrix, which is P, using KRT. So here we have K, which is our intrinsic matrix, R and T, which are our rotation and translation vectors, and P, which is our 3x4 camera matrix. So let's look at this first part. Let's look at line 27 and 28. Line 27, what it says is the 3x4 camera matrix. The first 3 blocks, 3x3 blocks, are going to be the rotation matrix, and the third column, which is this, so 0, 1, 2, and 3. So this is going to be our translation vector, and then we should get a matrix like this, which is our rotation matrix and our translation vectors. Now let's look at the final part of the code, which is star P equal to K into, so K is our intrinsic matrix, and now we are just going to add. So this is what the result we are going to get from this. So this is the last one function. Yep, that's it. Thank you.